This is just a quick summary of what we were talking about in the lecture on Gaussian quadrature. If you think about any of our integration methods, they all look like some number, which for us typically was delta x, in the case of the right-end rule or the left-end rule, multiplied by some function values. We then add up all of these things. In the code that we've looked at for this, we factored the delta x out purely for convenience, but if we felt like it, in order to think about these things, we could multiply it back through. Likewise, the trapezoid rule, which ended up being delta x over 2 times the function value at one end plus the function value at the other end times twice the sum of the intermediate function values, could be written as a number times a function value plus a number times a function value, and so on and so forth. Even Simpson's rule can be thought of in this way. So we'll have some x numbers. We evaluate the function at those x numbers. We multiply by some coefficient or the other, and then add all of them up. In a similar vein, we're going to have a new strategy. Previously, we used an interpolating polynomial, integrated that, and then used that as our estimate for the integral of f, either over an entire interval or on some subinterval. Here, we're going to select some numbers, r1, r2, out to rn. The n now is not the number of subdivisions in the usual kind of method. It's going to be the number of terms that I add up. The coefficients are c1 through cn. The approximation to our integral is going to be c1 f at r1 plus c2 f at r2, all the way up until you've accounted for the last one. In sigma notation, you could write it this way. This is going to be an approximate value for an integral. We have to figure out an appropriate way to pick these r numbers and these c numbers. Purely for convenience, we will pretend that we're integrating on the interval from -1 to +1. At first, that seems like an artificial restriction, but as we'll see shortly, it's no restriction at all. We want exact results if I were to try to integrate the constant function 1, also the function f of x equals x, f of x equals x squared, and as many of these as I think I can reasonably get away with. The new strategy is that we're going to pick these numbers, the r numbers and the c numbers, so that as high a degree polynomial as possible is integrated exactly. Now, of course, later on, it's likely that the a and the b are actually going to be xi minus 1 to xi, and we would be doing some sort of composite rule, just as we did composite midpoint and composite Simpson. I need to change variables. I don't want to do my integral in terms of x, but rather in terms of some other variable. When x is equal to a, I'm going to want this other variable to be -1. When x is b, I want the variable to be 1. Naturally, there's an almost unlimited number of ways you could rig such a correspondence up, but I want to be as simple as I can humanly be and still get the result that I want here. So, we'll use a small interpolation table. I have x values, a and b, and I'm going to have function values, which I will think of as being values of this alternate variable, u. When a is When x is equal to a, that is, I want the u to be negative 1. When x is equal to b, I want u to be positive 1. The Newton coefficient is 1 minus negative 1 divided by b minus a, which is 2 divided by b minus a. Parenthetically, if this is secretly integrating over a subinterval, this would just be 2 divided by delta x. The polynomial of degree 1 or less that's going to do what I want it to do is negative 1 plus 2 over b minus a times x minus a. As a sanity check, when x is equal to a, this term is 0 and u is negative 1, as it should be. When x is equal to b, in the second term, I have 2 over b minus a times b minus a. The b minus a quantities cancel out, leaving me with negative 1 plus 2. So when x is equal to b, the u variable is equal to 1, just like I want it to be. This is going to be my change of variables to put the interval from ab into negative 1 to positive 1. So in an effort to be clear here, the integral from a to b of f of x dx will be the integral from negative 1 to positive 1 with respect to x, except I have to write x in terms of u. I need function value f of x, so I have to have f with the x here, except I have to write the x in terms of u so that everything in my variable, everything in my integral that is now in terms of u and not x. Because u is negative 1 plus a constant times x minus another constant, it's not going to be very difficult to get a formula for x in terms of u. Firstly, add 1 to both sides, then multiply both sides by b minus a and divide both sides by 2. This leaves the x minus a by itself. Adding a to both sides, we now have x in terms of u. The derivative of x with respect to u is this constant coefficient. Dx is b minus a over 2 du. Again, if I'm secretly working on a subinterval, that would just be delta x over 2 times du. To integrate from a to b, f of x dx is now going to be the integral from negative 1 to positive 1 of f evaluated at a plus b minus a over 2 times u plus 1. Then the differential is b minus a over 2 du. Now, this looks very ugly and complicated, but it isn't. If you think of this as a function of u, all of those symbols are constants except that. So I could think of this as being some big complicated function of u, which is evaluated by adding the 1 to u, multiplying the result by b minus a over 2, and adding a. The way that we said we were going to do our approximation method was we're going to have various values, r1, r2, and so on, for the independent variable. We will have coefficients, c1, c2, and so forth, to go with them. We'll write a sum of one of the c numbers times what I get when I evaluate the function value at u equals one of the r numbers. So all we'll have to do is to put one of the r numbers in here, figure out this expression, feed that through the f function, and multiply that by the corresponding c number. So to keep the writing under control, I'm just going to think of having integral from -1 to +1 g of u du. I'm going to think about the simplest possible rule of this type. I will have two R numbers, R1 and R2, and correspondingly two C numbers, C1 and C2. I want to make sure that if my function g is the function that acts this way, you hand it an input and it returns 1 to you. I want to make sure that that is integrated exactly correctly by my approximation method. I want the integral from -1 to +1 of 1 du to be, I'm calling the function that hands you back 1 for an answer capital I, which made me think of 1. This integral is 2. These function values are 1, so I want 2 and C1 times 1 plus C2 times 1 to be equal to each other. This gives me an equation that relates some of the things that I want to know. So I now have one equation that relates two of the things I want to know. The things I want to know are C1, C2, R1, and R2. If I know those four numbers, I'll know how to do my approximation method. I've got four unknowns. If there's any luck in the world, I ought to be able to write down four equations for these things, and four unknowns, four equations. Maybe we can actually figure out what these things are. What if the function g of u were just u? The integral in question would be the integral from -1 to 1 of u du, and antiderivative is 1/2 u squared. U squared is an even function, so when I put the -1 and the 1 in, I get the same result, and when I subtract, I get 0 for an answer. On the other hand, I want that number, 0, to be the same as what I get when I do my approximation method, which is C1 times g evaluated at R1 plus C2 times g evaluated at R2. This time around, g is not the function that always hands you 1 back for an answer. G now does this. You put a number into it, and it hands you that number back for your output. The approximation method, then, is going to be C1R1 plus C2R2, and I want that to equal the exact value of the integral of u with respect to u. So this means C1R1 plus C2R2 needs to equal 0. I now have two equations involving the four unknown things that I'm interested in. One bad thing of note is I have variables multiplied by other variables and then terms added together. These equations are going to be nonlinear in general, which means I can't do something really easy like Cramer's rule to solve them. Pressing on, what if g was u squared? Antiderivative would be 1/3 u cubed. Put -1 and +1 into that and subtract. The exact value of the integral is 2/3. On the other hand, the g function is now just the squaring function, so my approximation will be C1 R1 squared this time plus C2 R2 squared. That number needs to be 2/3. I now have three equations. What if we try g of u equals u cubed? The integral has antiderivative 1/4 u to the 4th, which is again an even function. The exact value of the integral is 0, and if you apply our approximation rule to function u cubed, the approximation will be c1r1 cubed plus c2r2 cubed. If I want the cubic term to be integrated exactly by my approximation scheme, it'll be necessary that c1r1 cubed plus c2r2 cubed be 0. That's going to be my fourth equation. So we have 4 equations with 4 variables in them. It seems a little greedy to ask for more than that, so we'll stop figuring equations out now and look at this system of equations that we have. One thing that we've learned about numerical integration methods is symmetry is good. So I'm going to cross my fingers and make an assumption. At the moment, I'm going to assume that R1 is some number A which is positive, and R2 is the negative of that, so that these two numbers will be symmetrically placed about the origin, about 0. There may or may not be solutions for this system of equations that acts like that. If there is, I'll be happy because I will have found a solution to the system, which will define my integration technique. If something goes wrong and it turns out there is no solution of that system, of this character, then I'll think, oh well, it was a good try. Now I have to try to think of something else. If I put my assumption into the equations, the first equation didn't have R1 or R2, so it's still C1 plus C2 is 2. The second, though, is C1A plus C2 times negative A equals 0. The wheels in the back of your head should already be turning. C1A squared plus C2 times the square of negative A needs to be 2/3. C1A cubed plus C2 times the cube of negative A needs to be 0. In the first equation, C1 plus C2 is 2. In the second, I can write that as C1 minus C2 times A is 0. The third equation, if you square the negative of A, you get the same as if you had squared A itself. So that's C1A squared plus C2A squared equals 2/3. And in the last, if you multiply 3 copies of negative A together, you get the negative of A cubed. So the last equation now reads C1A cubed minus C2A cubed needs to be 0, and I like that one very much because it looks a whole lot like the second equation. In this equation, I'm hoping that A is some positive number. If that's the case, that says that C1 minus C2 has to be 0. C1 and C2 have to be equal to each other. Now that you know that, this first equation says C1 plus C1 is 2. Obviously C1 has to be 1, and C2 has to be 1 also. Even if I didn't notice that, I would have figured it out from the last equation. All I need to be true, then, is this, which we've already figured out what the C1 and C2 have to be. But even if I hadn't, I do know that C1 plus C2 is 2, so this last equation would say 2 times A squared is 2/3, which is going to tell me what A squared has to be. As a result, A squared has to be 1/3. Now we said A was positive, so A is going to be 1 over principal square root of 3. That's my R1. and R2 is the negative of that. So we now know C1, C2, R1, and R2. Our approximation method is C1 times the function at R1 plus C2 times the function at R2, 1 times f 1 over radical 3, 1 times f negative 1 over radical 3. I often like to write it with the R numbers in order from smallest to biggest, so if I wanted to do that, this would be my approximation method. This is the Gaussian quadrature formula based on 2 points. As a sanity check, I'm going to look at the integral from -1 to +1 of 3x squared plus 5x plus 2. This is a polynomial of degree less than or equal to 3. The way integrals work, this is the integral of 3x squared plus the integral of 5x plus the integral of 2. And again, because of the way integrals work, that would be 3 times the integral of x squared plus 5 times the integral of x plus 2 times the integral of 1, each one of which my approximation method gives me the exact result. So I plugged -1 over radical 3 in for the x, I plugged 1 over radical 3 in for the x, multiplied function values by C1 and C2, which are 1 in this case, did the arithmetic on my calculator, and it said 6. The Gaussian quadrature approximation for this integral is 6. On the other hand, of course, if I want to do the integral using Calc 1 techniques, the antiderivative is this. Write out the difference of the two antiderivative values. It ends up being 2 plus 4, which is 6, just like it's supposed to be. If you look in tables online or in the textbook, you'll see values of the R numbers and the C numbers for methods that are based on more than 2 points. But this is about as far as I'm going to go into this. I didn't feel right just leaving Gaussian quadrature out, so we have had a simple discussion of it. I hope everyone's doing well. I'll talk to you again soon.